Hello, this is Matthias.
Hi, everybody.
Hello, this is Matthias.
Hey, Matthias, how are you?
Hey Rob,
Good.
I'm gonna be on somewhere in the car, but I just want to say hi.
Hi there. No problem. Mehdi, how are you today?
Doing good. How are you, Rob?
I'm just,
everyone.
go ahead. I apologize. I had another call that ran much longer than I anticipated, so.
Oh, that's all right. So is Matthias is here, right? Yep.
Yes, I saw Matthias. We can wait a minute.
Sure.
And then we can, whatever you guys would like. Let me get my headphones. We'll start here in another minute.
Good morning, Mehdi.
Hey, Martin, how are you?
Doing well, and you?
I'm doing good. Thanks.
Morning, Rob. Good morning, everyone.
Hi, Martin, how are you?
Not bad. Not bad.
I will just one brief personal note. I was pleased to make it through my both DAC, where Mehdi and I met for the first time in person. That's the reality of these times, and then also my son's wedding without contracting COVID. So I declare victory on that note. But anyway.
Oh, wow. Yeah, it's certainly gotten a lot harder in the last couple months. I remember I didn't even think twice about it when I went to International Memory Workshop, maybe 3 months ago, but it's much different now. So congratulations.
Thank you. Thank you. Why don't we go and get started? So today, Matthias is going to give us a presentation on KLayout. Koefferlein, am I saying that
Yes.
correctly,
Yeah.
Matthias?
That's correct.
Thank you. I did study German for 7 years, so
For 7 years. Okay.
I know my umlauts.
So I'm going to keep this talk in German. So it's, okay. No, don't worry. I mean, I hope my English is good enough. So it has a lot of strong German accent. So well.
My general experience when I have had the fortune of visiting Germany or Austria or Switzerland is that folks' English there is far better than anyone's German in the U.S. But I do appreciate the opportunity to practice, and everyone's been very kind and patient with me in that regard. So, Mehdi, is there anything else you want to?
Not really. I'm looking forward Matthias' presentation.
Okay. Yeah, so I mean, I can start right away if you like.
Sure. Yes, that'd be great. Thank you.
Okay. So yeah, let me share my screen. I hope this is working because I have never tried so far. Can you see my screen?
Yes.
Full screen? Okay.
We have it.
Well, very good. Yeah, to be honest, I don't know exactly what you folks are doing here. But the story is I met Mehdi in Paris when we had a small conference. When we had a conference, maybe not even a small one. And it was basically general open source, EDA, silicon, and so on. And I think, well, I was one of the organizers, so I had they gave me some room to talk about KLayout, which is a, let's say, a quite popular tool in that area. And and there was some interaction with the people from GDS Factory. I had some collaboration, I'd say, in the past. So we are currently building together some better integration in these workbooks, the Jupyter workbooks. So we have a nice viewing ability and maybe also processing speed up for them and so on. So there was a lot of interaction already, and I understand that basically this is the direction from which you come.
I think it's I think you basically summarized it. It was great to see your talk. I've been using KLayout for a while. I think a lot of people in the open source community are using KLayout. And the reason I wanted you to present here is that KLayout is, or GDS Factory is what I've been using 70% in my PMU block. So I was thinking it would be great to know the real, tool behind GDS Factory and get to know you as well.
Yes, that's at least an opportunity now. I think some of you I know already met. I guess I met a couple of years ago. We also had some exchange about LVS and DSC. I also saw that Mariana is in this community. I don't know whether she's joining today, but she has a workshop on BAG currently, or mainly focused on trying to ramp BAG. So there's also some interaction here. She approached me a couple of times before for certain things, ideas she has, and so on. So I think there's some overlap. Honestly,
Mariana. Mariana does participate in this group, and she did kindly advise that she herself was not going to be able to attend today's seminar, which she had hoped to. But I do know that some of the folks who are participating in the boot camp there, I think they're holding it in Austria. I don't know the exact location, but irrespective, but that they may attend today. So anyway.
Yeah. Okay. Anyway, so this is the, let's say this was the motivation, and I mean I was kind of curious. So I was basically told that you might be interested mainly in the topics of layout generation. So I'll talk briefly about the project in general, and then maybe a few words about how KLayout can support generation. And then there's also a few words about parasitic extraction, but I hope I don't disappoint you, because actually currently there is not much there feature-wise, but I have been approached many times about parasitics, so maybe I can share some thoughts about parasitics extraction with you, and then we can go into a discussion, I'd say, because this is mainly what I'm here for. Okay, so for those who don't know this project, actually it started around 2009, so it's already pretty major, I'd say. It started eventually as a viewer for GDS files or layout files in general. I published it under GPL after briefly considering to go commercial, but that was a bad time. That was a financial crisis, so I didn't do so. So I just published it, and GPL was my license of choice because the Qt framework required me to pick GPL, and that's still how it is today. So it's still GPL. It's entirely open source. I have added many things since then. So first of all, there's now editing being added, or had been added. Scripting abilities were added. P-cells were added. Many more file formats. A lot of APIs. And finally, DRC and LVS support, which grew over time into some hierarchical support even. There is a standalone Python module now, which is published on PyP. And this is the one that, for example, GDS Factory is using, but I also think many others are using as well. Plus. So the list is quite long. Had 13 years of development. It's still actively developed. So I'm doing a lot of maintenance. Unfortunately, this grew so much that I have to focus now on certain areas. But I can, let's say, already announce here that parasitic extraction is one of my focus areas I want to focus on. So I hope that aligns with your agenda. The strengths of the tool, I'd say, as it started as a viewer, at the time where I started the project, I was working for Qimonda, which was a Munich-based DRAM company. It died 2010 in the course of the financial crisis, but they made DRAM products, and the characteristics of DRAM is that you have to work with large GDS files, specifically when you deal with post-processing files. So when you have OPC applied and you're dealing with mask data, then we are easily in the range of 10, 20, 30 gigabyte of GDS. So, and that was my main focus. So I wanted to have a tool that is capable of handling this complexity of layout files. So the strength is definitely a compact database representation. It's quite fast in loading and viewing, so you can view big files. I mean, I hard to say where's the limit. I myself loaded like 60, 70, 80 gigabyte of GDS already, so it's still usable, provided you have enough memory. And I also consider the algorithms built in for layout processing and analysis, specifically the Boolean operations. I consider them pretty robust. I'm using them myself a lot, even for non-Manhattan geometries, where most of the algorithms available so far are either slow or they don't work at all. Another strength is definitely the integrated scripting engine and the debugging and the IDE facilities, which hopefully make it easy to develop your own scripts. It's an alternative, so you can still use PyCharm or any other IDE you want. And I think also that the tool has now become a de facto standard for viewing GDS and Oasis. So feedback I get is that wherever you go, whichever foundry you go to, they are all using KLayout for viewing their GDS files. So apparently, I have no numbers, I don't track users, but I think basically every company uses it in a way. So there's definitely a widespread distribution happening. I also think that the Python and the Ruby API for scripting is pretty rich now. I mean, there are sure features missing, but it's already quite elaborate and also quite complex. So I think you can do a lot with that. I'm also quite proud on the viewing abilities because many viewers you see, many commercial viewers even, they tend to optimize away features once you enter a very big zoom range. So in order to speed up viewing, and this is, to my personal taste, this is not acceptable because if you're trying to find a single polygon in a huge layout, which maybe is the error marker you're trying to locate, then you want to see every detail because otherwise you're searching for the needle in the haystack. And KLayout is definitely in that sense a high fidelity and high quality viewer, if not the best one. And there's also a good support for many other file formats. I need to say that I focus on open file formats, of course, because whenever I want to implement a file format, I need to make sure that the specification is openly available, because otherwise I might encounter problems with IP violation. If a specific format is protected, then I basically cannot implement it in an open source tool. But still, most formats are maybe not well documented, but openly available. So like DXF, and they are supported decently, I'd say. Of course, there are limitations. I mean, currently the tool is a geometry tool, so it's focused on mask layout. It's not a design system, I need to say. So some people think it's a kind of virtuoso light. I don't think it is, because it's basically lacking a net annotation of all these nice advanced features you're being used from Virtuoso, specifically schematics entry and also editing aids like automatic via placement, place and route, and so on. Things you need to have when you want to create bigger layouts manually. The performance and the memory footprint of some DSC features definitely needs improvement. So if you put in a huge SRAM or if you put in a very large SoC, then it's you probably better still use Calibre. So KLayout cannot compete with Calibre in that respect. But I'm working on this, so it mainly depends on the availability of test cases which are good enough to reproduce performance issues, and usually I can do something about performance. Yeah, another limitation is that the whole thing is a single-threaded UI application. I mean, it doesn't mean it cannot utilize multiple cores in general, but it means if, for example, while you run a DSC, the whole application is blocked. That is different in, let's say, other or modern applications, but there are ways to work around. And the current DSC and LVS implementation, it's pretty basic, or the basic features are there. You can do a lot with that already, but the commercial engines have a few advanced features. For example, connectivity-based DSC rules, which KLayout does not have yet. But that's also on my to-do list. And like I said, currently parasitic extraction is not part of KLayout. This is something I want to just show you to give you some impression about what this means internally, what I just mentioned. So one key feature is memory compactness when loading big GDS files or big layout files in general. So KLayout tries to store the objects in a very compact way. So like on the left side, you see when you have a rectangle, you can store it in a few bytes. If you keep them in a contiguous memory layout, And this is first very fast and very compact. It needs little memory. You can play some more tricks on that, like you can cache points for polygons and text strings. You can also cache. You can build efficient quad trees for region lookups on these structures. And when you load Oasis, this is an advanced format which is sometimes regarded the successor of GDS. Oasis features shape repetition, so it's very, very efficient to represent regular arrays of shapes. And KLayout can store these features in memory, so you need not much more memory than the Oasis file itself takes. Compared to that, on the right side, you see some classical object-oriented tools. I don't say names, but they probably work with something like doubly linked lists. They use type information, attributes, and so on. And this overall takes a lot more memory than storing it compactly. On the other hand, this means that KLayout has an API which is not typically easy or as easily accessible as, for example, open access. So the access methods are a bit more they are a bit indirect, so I cannot directly manipulate an object. So that's why the API first feels a bit more clumsy and strange if you come from open access, but I think you get used to it. And finally, I think there's no real disadvantage of working with a compact layout model or compact memory model rather than an elaborate one, except that you have, of course, much less memory requirements. And performance-wise, so this is an example I took from a SoC layout I had. So this is 1.5 gigabyte, and it loads in a little more than 7 seconds, and it takes 750 megabytes in memory, so which I consider pretty good. So I can load these kind of layouts on a week-old laptop, if you like. The drawing engine built into KLayout does not utilize OpenGL or any hardware acceleration. Still, it's quite fast. So this means it's compatible with all kind of hardware. Specifically, it runs on virtual environments where you don't have hardware acceleration. It's based on a bitplane rendering. So every layer is rendered on a bitplane. And then these bitplanes are composed into colorful images. And this makes it very fast to change layer attributes or hide layers. There's a lot of optimization built in, like cells, for example, are bitmap cached, and quads from the quad tree are skipped if they are smaller than a single pixel, and so on. And in the end, the quality is quite good because whenever there is something, you will see at least a single pixel highlighted. The drawing engine also supports a lot more. For example, you can add images to your layouts, which I think is used by people, for example, who investigate layouts together with SAM images or microscope images. So it's very convenient. You can align these images with the layout and then look for defects or whatever. Regarding I/O, these are the file formats which are formally supported currently. I tried to kind of indicate the quality. So ++ means it's very well supported. - means it's decently to weakly supported. So DXF is not my favorite format. That's mainly because DXF is a pure drawing format. And it's badly documented. In fact, it doesn't even have units, so you never know if you get a number, whether it's micron or millimeter or whatever. So this kind of works, but I don't recommend using it. The other formats are quite well supported, I'd say. The left-def is supported, and here we come to Open Road, which I also understand is important to you as an interface or for interfacing. And they use Magic and left-def as far as I know. Left-def is also not my favorite format because it's made in a way it's not extensible, and you always need to follow up if they enhance the specification. In parts, the documentation is quite decent, but still it's partially difficult to understand what it means. And it basically took years for me to debug it with the help of many users. And I think what is currently available now is a pretty stable implementation, but it does not take the net information. It just translates the geometric information, the polygons, into something that is GDS-like. Writing is supported for most formats except for Java and LeftDev. Well, LeftDev mainly because net information is missing, so there's little use in LeftDev if you don't have nets, but also hierarchy is not easily representable in LeftDev. Scripting support. So KLayout offers two scripting engines, which are both built in, so they coexist. One is Ruby, one is Python. So my personal favorite is Ruby, but many users prefer Python. It's because of its simplicity. You have an in-application way of doing scripting, but there's also an out-application way. It's via the KLayout module, which is available of PyPy, which I already mentioned. It's essentially a copy of the code which is available through KLayout, but it lacks some of the APIs which do not make sense in a standalone environment. Everything that's user interface related. But recently I ported the whole rendering engine into this module, so you can render to some bitmap, and this works because there's no hardware dependency, so it's a pure software implementation, and the bitmap is essentially something that is doesn't need any user interface. So technically, you can render to a PNG file and display this, for example, over a WebSocket interface. So there's a demonstrator which shows that you can run basically a Python module-based KLayout in a web server this way. There are many applications for scripting, so many people use it to code user interfaces, so their own dialogues, their own well, applications. You can do a lot of layout analysis with scripting, so the whole DSC engine is more or less available in terms of low-level APIs. You can build domain-specific extensions, so specifically in Ruby, it's very convenient to create something that looks like a different language, but essentially you're executing Ruby. And for example, the cross-section application, which I also showed in Paris, it's an in-application extension which you can use to generate virtual cross-sections for a layout. So it shows the metal stack or whatever you want to see. You draw a ruler and then it displays the cross-section. It needs a setup file, and the setup file is essentially one of these DSLs, so domain-specific languages that can be easily done using the Ruby interpreter. You can think of any other domain-specific language if you like. Many people use scripting, of course, to code P-cells. So I think you're familiar with P-cells. If not, P-cells are basically parameterizable cells, which you can, you can use, for example, to code devices. So a device is given by a certain number of parameters, and by using a P-cell which represents such a device, I can basically generate variable cells. I just enter the width and length of a transistor, and the P-cell will generate the transistor then. And this is also available in KLayout. Slightly different, and this happens in Virtuoso, for example, but in a quite similar. But in the end, the concepts are pretty much the same, and I find many people can reuse their knowledge they gain from Virtuoso coding also in KLayout. And of course, finally, scripting can also be used to generate layout. So you build a GDS file out of nothing, just using Python or Ruby code. And this is eventually the way that GDS Factory goes, with some add-ons, of course.
Hey, Matthias, you may have a question. I don't know. I
Yeah,
see
sure.
that someone raised their hand. Akilas, do
Oh.
you have a question?
Yes. Hi, Matthias, and thank you. Can you put the exactly? So with Python and this KLayout module,
Mm-hmm.
we can access to all the functionality that KLayout provides. Yeah.
Yes. So 80%, I'd say.
How?
Yeah, 80% of the functionality you can access through this KLayout module. So not every single API is available. Everything that is related to user interface.
That means that we cannot render things like in the screen, but the things about the layout generation and the analysis, all of that is included.
That is included, yeah. And there's even a discussion ongoing how to include DRC functionality. So true, yeah, I mean, DRC is available because the objects which are used to generate, to implement DRC are included in this module, but not the DRC language itself, because that is Ruby. Nevertheless, there's a discussion ongoing how to port this to this DRC language to Python, and maybe you will finally find DRC also available in the Python module. And regarding rendering, that we discussed an extension, or I have created an extension which is currently experimental, but there's a branch on GitHub where this is available. And with this new version, you can essentially render layout to a PNG file with using this KLayout module, but not using the Qt libraries. And this is what I meant. I'm not sure. I think I could have prepared a demonstration of this, but I didn't. So I think I will not get it running so quickly. But I think you just have to wait a little, and then there will be some development happening in the for GDS Factory. I think they are already picking this up, and hopefully will release this sooner or later.
Yeah, I put the link
Thanks,
in the chat.
Matthias.
Sorry?
Thanks, Matthias.
Okay.
And
I put a link on the chat. So in the chat, I put a link that you can describe your DRC rule decks in Python.
Joking. Okay.
yeah. Thanks, Joaquin. I've already copied.
You should have told me you're in here, so you could have explained even better than me. Okay. Yeah, I mean, I know. So, well. So, how many of you do know me already? A couple of, but.
Yeah, I know you.
Okay. Yeah. Well. Okay. So there's going to be some development. I don't see the chat here. Sorry. So I just see who's talking. Okay, so regarding the APIs that KLayout offer, this is also basically answering your question, I hope. So there are a couple of different, I wouldn't say they are these APIs are not disconnected, but there are some APIs or some group of functions and classes that form individual APIs, and there's an application framework, layout database, DRC, reporting, Qt, binding, geometry, and so on. And as you see here, so the ones with the green circle, these are the APIs available to the KLayout Python module. And in the new version, also the left top one also is partially available. So there's a good coverage already, and I think this this will give you a lot of more options as compared to what you have already. I think for you, for the application of layout generation, I think the layout database and also the geometry engine are probably the most important ones, because they basically comprise something that is similar to, yeah, I wouldn't say open access, but maybe the layout part of open access can more or less be mapped to these APIs. And regarding the geometry processing capabilities, I'd say that KLayout is even much stronger than open access, because you have Boolean operations and things like that, for example. Coming to layout generation, because I think that was an important point for you. There are multiple options to do layout generation. One is p-cells, as I explained. So p-cells are usually used for creating small and small layout features such as devices. I mean, they can be big in terms of area, but they are not big in terms of complexity. So I don't think anyone would code a p-cell for a flip-flop, for example. So they would code p-cells maybe for single transistors in the extreme case, including finger transistors or things like that, but not much more. And they're very convenient when you generate layout manually, because they're integrated in the layout editor, and you can adjust parameters and immediately see how they behave. In KLayout, you can code them both in Python and Ruby, and they can both interact. So it doesn't basically matter which language you're choosing. So Python layout generators can use p-cells coded in Ruby. So there's a bridge built in. Then there's a low-level API where you have all the commonly used objects like cells, shapes, polygons, paths, instances to place cells, and so on. And these are the building blocks where you can build any kind of layout from whatever you want, provided you have the algorithms to do so. And then there's a slightly higher level API where you have Boolean operations and layout processing operations, things like Minkowski sums, corner rounding, dummy fill, DRC features, or can even do width and spacing checks if you like, things like that. And this also includes net tracing and net extraction, which is essentially then the basic feature for LVS. So you can, yes, sorry.
For the net tracing, so is there any feature for connectivity, especially when you're drawing polygons, right? It's kind of really hard to track how everything's connected.
Yeah, it's
so
not okay. It's not integrated into editing currently, mainly because there's no schematic that you can attach to. But for example, there's a feature which is the net tracer. So you click, you have to define your metal stack, then you click on a metal piece, and then it will show you where this metal routes to.
I see. So it connects all the polygons together that are supposed to be connected
Exactly.
to VIAs.
So,
oh, that's
and
good.
it will highlight this net. And this is quite convenient if you want to see whether you created a short or something like that.
Yeah.
But it doesn't happen immediately, so you have to trigger that. And if you happen to touch a VDD net on a big sock, then it takes a while. I mean, you can stop it, of course, but it basically works. You can even extract a power net or ground net from a big SoC, but then you wait an hour or so.
I see.
Yeah.
But how can you enable this? It sounds like there's some procedure to have here, right?
I mean, do you mean in terms of scripting, or do you mean from the user interface?
Yeah, from the user interface, or if there's some API I can use that is already available.
No, there's a menu function which is called net tracer. It's available in the tools menu. You need to set up a layer stack. There's a button.
I see.
If you search for net,
I can see it now. I can see it.
Net, yeah, exactly. So
thank you.
Yeah.
There's about 20 minutes left, by the way.
Okay, yeah. So, I mean, I'm basically, I don't have a lot to say. Most of that I've told you already. Most content is already presented. I've just wanted to show you a few examples for layout generation. This is an example for a P-cell I coded. This generates a QR code. And basically you type in a text and then it will generate this QR code on the fly. So, and this is already an example for a complex P-cell and it's openly available. So whenever you need some feature like this, you can code it for a P-cell, and you can also use P-cells from scripting. So you can embed this P-cell in a layout generated by a script. This is a simple script example which shows how to use the low-level API to generate layouts. In this case, it's creating a couple of labels. Things like that you might need when you create test structures where you want to investigate LIFO effects or things like that. Then you might want to have labels, and below, I will not explain now how this works, but this is basically a small Python script which generates this field of labels using a P-cell, a built-in P-cell, which provides these texts. There you can see that with a few lines of Python, you can already create complex layouts with variations built in. And this is another example. You can also generate layouts in terms of region features. Regions is in KLayout what is called a layer in Calibre. So it's essentially a set of polygons. And here, this example uses this feature to generate a kind of guard ring with rounded corners around these pinkish shapes. And to do so, it uses sizing operations and corner rounding and things like that. And this is actually a DRC script. So in this case, the DRC does not check anything, but it's used to generate layout. This is also a way to add or to manipulate layout. So for example, in this case, to add features which may enhance manufacturability, for example. So this is another way of generating layouts. Unfortunately, so far, that is what is available, which probably is not enough if you talk about higher level concepts. For example, if you want to have place and route, I imagine if you want to really generate a circuit, then of course you need to have some place and route feature built in. Right now, KLayout does not support a place and route function that you can readily use. But I think there are many algorithms available out there which probably can be implemented more or less easily with the features or with the functions which are there already. It's basically a matter of trying, I'd say. I don't have a list myself what is there, what projects are there, what could be basically candidates for such a thing, but I'm quite confident that looking for such implementations, you will find something. I also would like to raise the question if there is need for certain support features for this. I personally have little experience in implementing place and route place and route algorithms. But maybe something like a point stitch data structure, for example, would be useful in this case. Maybe it can be added to KLayout itself, or it can be added as a Python module with a way to translate between polygon geometry and so on. So I'm open to discussions here if you have an idea how to proceed here.
What is KLayout itself written in? What language?
It's C++.
C++, okay.
C++, yeah.
How hard would it be? So to your point, which is, I guess, what asked my original question, but if one wanted to add like a placement engine or a routing engine using some of KLayout services. How hard would that be, do you think?
I would personally try to kind of link it through Python. So if your place and load engine is available as a Python module, then it's probably possible to link that to KLayout.
Okay.
Yeah, it's like I think we're doing something kind of along those lines with the Coriolis project.
Yes.
So and obviously, Matthias, we've discussed before, like potentially doing what could go into a common database that we could use across all these different parasitic extraction and schematic and place and route.
Exactly. Yeah. So that's
it's a long journey.
It is in fact. I mean, my understanding is that many databases are kind of specialized, but if there's something that is, let's say, generic enough, then and you have different tools able to attach to it, of course, why not KLayout and any other tool like Coriolis and some parasitic extraction tool if you like.
Exactly.
Okay, so regarding pin terminal information, I just wanted to mention this because this is quite a crucial ingredient for many higher level circuit generation features. So you need to know when you have a sub-circuit where the pins are. KLayout currently does not provide data structures for this information, but of course it can be added if required. Okay, so now coming to the last topic, which was interesting for you, I'd say, or I heard at least. Right now, parasitic extraction is not a feature. We talked about this many times, so me and others, and even I don't remember the name, unfortunately, the guy from the fast solvers. We were talking already. Honestly, I couldn't really find an access to this topic. So there are so many different levels of detail you can consider. So starting from very simplistic models to three-dimensional EM simulations and so on. So I think it's important to first focus on some scope. And I understand that most implementations we have, including, let's say, OpenRCX, are pretty use pretty simple models. But honestly, I tried to understand OpenRCX, but I didn't get far. To me, it's a bit hard to read.
Have you come across TasYargle?
Yes, I think I had this. I even downloaded the source code.
Yeah, because we did a bit of cleanup on it because some of the code's really old. But because that was used for Bull when they were doing the microprocessors. And like probably bottoms out at 90 or something.
Yeah, I would need I would need to know the theory behind that. So just reading the code is always a bit difficult. But I understand there's probably some concept behind. So if you have references, please. So anything is welcome. If you have some.
I think Jean-Paul might be able to provide a bit of guidance. I'm not sure.
I think I'd asked him already, but maybe he said it's in French. That's not my comfort zone. I don't know.
Yeah, that's one thing with TasYargle. There's a lot of French commentary in it.
But I understand. I mean, also, so Tim Edwards was talking about his attempts to do RC extraction, and he was a bit skeptic. So I think he was not really content with his success he made so far, which kind of shows me that
magic?
it's not that easy.
Are you
myself?
Are you referring to magic?
Yes.
I see.
Yeah, Tim made some at least some attempts to to go in the direction of RC extraction, but he was a bit skeptic. But finally, he achieved like 20% accuracy from a with very basic assumptions, so which I consider quite good. But he was not happy with that, so I don't know. At least on Skywater, he was focusing on Skywater.
20% accuracy, you say, or 80%?
No, he said 20% accuracy, but in timing it was like 50% or something like that.
I see.
Yeah, but his assumptions were only material properties and geometries and nothing else. So, I mean,
so this is just RC extraction, not device extraction, right?
Yes, exactly. Yeah. So
okay.
This is about parasitic extraction, device extraction. I mean, I'm thinking of device recognition or device.
Well, I'm just thinking about just device parasitics.
Yeah, I think that.
Yeah.
That's a whole other world. Sorry, go ahead.
Yeah. Yeah, I mean, device parasitics, if you think, for example, about the fringe capacitances of well or of the source drain regions or things like that, I guess that's pretty simple because you extract the area and parameter of source and drain, and then this goes into a BSIM model, and that's it. I think it's more complex if you talk about devices like inductors or devices like capacitors, MIMCAPs, or things like that. Is this what you think of?
Right.
Yeah,
I think we need to do. I think it is important to have some qualitative numbers on how bad is parasitic extraction in these open source tools. I mean, I mean, especially Magic, because that's the only one we have right now for device extraction. And
do you think of parasitic extraction for the purpose of analog design?
Yes.
Okay,
correct.
so it's not just about timing.
Well, I mean, I think there is timing issues with OpenRCX, and there is a calibration that is being done right now that isn't pretty fully open source. But that's a different issue than just basically simulating your op-amp or LDO.
I imagine that for this you need a really well cross-coupling enabled and a detailed netlist with RC elements and so on. Maybe a reduced one, things like that. So you cannot just take SPEF, right?
Yeah.
Yeah. So, I mean, honestly, I have some experience in using parasitic extraction tools, but not in coding ones. So, I mean, if there's some literature or some basic ideas how to do that, I'd be happy about this. I mean, I can show you. This is essentially my these are my thoughts about this. KLayout has a little bit of support already for this kind of feature in terms of providing the basis, so it can give you because it needs that for LVS, it can give you a netlist which has a link to layout, so it can give you the polygons from a net, and you will get the hierarchy of circuits and the devices and the multi-layer geometry. So this is available. And you can essentially also identify nets that interact in terms of a certain interaction distance, collect the geometries, and then go into some heuristic RC extractor, if you like. And finally, you could also attach timing information to these nets. That infrastructure should be there already. And this is an example I took from a real layout. This is a single net. And from KLayout, you can essentially get all the polygons which make up this net. And you see here these bluish elements. So these kind of hooks or these leaves. These are the device terminals, so the sources in this case, because it's a VDD net. And the green and the reddish elements, these are the metals. And of course, there are vias built in. And KLayout has this information. So, for example, if you think about now generating resistor networks from this, that's the input. So if you have a magic algorithm that comes up with resistor network from that bunch of geometry or this bunch of polygons, then just hand it over and I'll implement it. I just don't think such a thing is readily available.
Yeah, that would be great. I think Joaquin has a question.
Yeah.
Yeah, I have a question with net tracing. Like the way we implemented NGDS Factory is using these Epic tools where they draw a device recognition layer and some pins. And the pins are basically making sure they overlap. But it doesn't really track layer to layer, like different metal layers connectivity. So you were saying, what's the recommended way to implement netlist tracing? Do we have to add labels or?
So I think what you refer to is essentially coming from photonics, right? Where you don't have vias, I understand.
We have multiple layers of metal. So it's basically, you can think of photonics as basically a CMOS chip that basically we just throw some photons on, but at the same time we need to connect electrically to those diodes and
yeah, I mean, so labels you don't necessarily need, but it's good to have a label because when you debug, you know which net you're looking at. I mean, apart from this, a network connectivity is essentially quite simple. So it just tells you what metal layers you have and what vias connect which metals.
And you define that in your technology, or where do you define your metal stack?
Yeah, in this case, I took the LVS engine. So the LVS engine it's made from a couple of phases. So the first phase is to derive the layers which you need. So for example, of course you read in all the metals, but then you also separate the gate areas from the other poly regions, and then you need to subtract gate from source drain, for example, to separate source and drain, and so on. So you have a kind of preparation phase, and then you take the outputs of this preparation phase and you start connecting it. So everything that touches needs to be connected. For example, the metal 1 via 1 metal 2 transition, you connect metal 1 to via 1 and via 1 to metal 2, and that makes a connection over the via, and so on. And in the next step, you then extract the devices, which is a separate step. You need then to have an idea of what is a device and where the terminals are and what devices you have. And this will generate you these terminal shapes here. And then you finally extract the whole netlist from that. And this gives you then a schematic or a SPICE netlist or a netlist API structure. And KLayout knows what original shapes were connected to each net. And you can regenerate a layout from this information. And this is what I did here. Is this answering your?
Yeah. The main issue I was having with the current connectivity checks that we use with Epic is that it doesn't really scale very well with the layout side. Okay. So maybe I think for that, the hierarchical mode, or I think you covered this at the Free Silicon conference. Maybe running on a different mode will be better because it works well for small circuits. If we make a bigger circuit, the connectivity checks with this, because the LVS engine or the DRC engine, if it's too big, there's too many booleans.
Oh, that needs to be very big. Yeah, maybe can you supply an example so maybe I can take a look?
Sure. Yeah, I'll send you an example, and that starts to be slow. And but maybe we can fix it with your net tracing. I think that would be the way to do it.
I suspect a little because you have these kind of curved round features, right?
Yeah, that's the problem. Maybe I simplify the polygons will be better before we.
Well, maybe there are some easy switches I can show you.
Okay.
If you send me an example, I can take a look. If you have an example, you can share.
Perfect. Yeah.
We're coming up in the hour, by the way.
Yeah. Okay. Sorry. Yeah, I'm done basically.
That's okay.
Yeah. Well. Okay. So
very good. No, thanks.
that's only links and Thank you.
Yeah, thanks, Matthias. One thing I wanted to just add is maybe we should think about a way of having some regression tests for this PIX extraction. If there's a way, if you think there's a way we could do that and provide example and build something, that would be really helpful for the whole open source community. Because I think that's one part where we are a bit struggling and we don't know if what is golden, to be honest.
Yeah. I mean, when you talk about regression tests, do you think correlation with actual hardware as well?
I think so, right?
Yeah.
Like if we have, I mean, we taped out ring oscillator and test structures with NIST, so we can use those, and you have the layout and netlist, and you can build on top of that, right?
Did you tape out ring oscillators with parasitics included? So like capacitors?
Where we did line resistance and VR resistance.
Line resistance.
So yeah, so those should be good. But we didn't include RC in the ring oscillator. We just put them next to each other.
Okay, that's at least some data points that you could evaluate. And I assume we're talking about Skywater or something like that.
Correct. But we're planning to do that for the other nodes. So we should probably resume a discussion offline and see what could be done.
Yeah, I mean that's at least that's important for modeling. Honestly, I don't know how to generate a real test suite that covers many cases. I mean, maybe you also need to include something like analog blocks, like or DLLs or something like that.
Yeah, I mean, there's a couple now. I'm pretty sure we can leverage a couple designs from what was taped out. I'll talk with NIST as well and see if there's a way to do this, a better way or some kind of approach.
Yeah, direct measurements are probably difficult to do. You hardly get any picofarads or something like that.
Yeah. So let's follow up, I guess. Thanks, Matthias, for the presentation.
Okay, you're welcome. I mean, well, it was kind of just a quick walkthrough.
Yeah, I think it's great.
No, it was great, Matthias. Thank you so much. Really appreciate it.
Yeah, so at least you know who I am, but most of you know me already, or some of you do. So I understand. But it's not a big community. There's still too few, let's say, to really leverage some huge projects here. But it's things are evolving, definitely.
Thank you so much. Appreciate it. And thank you everyone for attending today too.
Okay, so
thank you.
Well then, thanks, and well, enjoy your day. So for me, it's evening. I'll enjoy the evening. Okay, bye.
All right. Thank you. Bye-bye.
Thank you.